So we'll continue our discussion of Zener diodes today. We'll look at a load line analysis of the Zener diode, and then the important application of a Zener diode as a voltage regulator. Okay, so we'll do both a load line analysis of a Zener regulator. We'll also do an analytical analysis of the Zener regulator, and it'll be kind of like a design problem, right? So let's get to the class notebook. All right, Zener regulator. Chapter 1. This is where we stopped. Okay, so we have a Zener diode. Zener diode is simply connected to a supply voltage VSS and a series resistor R. Okay, there is no load RL, not for this analysis. We are simply doing a load line analysis where you have a supply voltage, you have a series resistor R, and a Zener diode that's connected. Okay, so if we want to do a load line analysis, and this is right here on the next page, so we'll graph and plot it on there. Let's look at first the given quantities. We are told VSS. We're told VSS is 15 volts. This is the load line analysis. VSS is 15 volts. Our resistor R is 1 kilo ohm. And we are asked to find the output voltage. We don't know what the Zener diode is. And in this case, we actually don't even care about the specs. But what we are given is the diode characteristic. So the diode characteristic is given to us. Okay, that's on the next slide. So based on these, we need to find a solution for the diode voltage and the diode current. Now, if you recall the load line analysis for the PN junction diode, it's two quantities, voltage and current, two unknown quantities, meaning we need two equations to solve it analytically. Or if you're trying to solve it graphically, then we need two plots. One plot is given to us, we need the second one. The second one comes from the line of the linear portion of that circuit. So we isolate the Zener diode away from it, write a KVL expression, and plot the line. Okay. So if we write the KVL expression, we would get VSS. In this case, I'm going to follow my sign convention. If I apply KVL, I obtain minus VSS plus VR minus VD is equal to 0. And as I've stated earlier, everybody has learned KVL and KCL in prior physics classes in 201. And at this point, every student has their own preferred method of applying KVL. Okay, so stick with what works best for you. Do not feel compelled to what I do. Okay, but an explanation about this. If you can see the circuit, what do we see? Supply voltage VSS, there's only one source in the circuit. So it must drop, that supply voltage must drop across the load resistor and across the Zener diode, right? So even with just visual inspection, we can state supply voltage should be equal to the series resistor VR and the Zener voltage VZ. That's it. VR plus VZ. That's our KVL. But Zener diode is connected in reverse bias. So remember last class I stated, even though we say VZ is positive, if you are referring to diode voltage and diode current, anode is positive, cathode is negative. So VD would be negative, ID would be negative. And it's represented in the graph in the third quadrant in reverse bias because it is reverse bias. You all with me so far? And that's why I have the sign as minus VD and not plus. Okay, so keep that in mind. All right, so if I was to expand this, I want to find diode voltage, diode current, two quantities. And if two quantities, they're the ends of the line, the assumption is a linear line would intersect the X and Y axis somewhere. So VD and ID must be zero at some point. So I could write this is minus VSS, and this VR would be minus ID, because ID again is flowing in the opposite direction, times R minus VD equal to zero. Plug in VD and ID as equal to zero and find the corresponding values for the two endpoints of the line. So if we plug in VD equal to zero, we find ID. And if we plug in ID is equal to zero, we can find VD. So ID would be minus VSS over R, which comes out to be 15 milliamps. And VD simply comes out to be minus VSS, minus 15 volts. So let's take a pause, write it down. Let me know if you have any questions. Yes, that should be a negative. Thank you. In general, of course, the plus and minus sign is for us humans to balance out our equations, right? We already know that Zener diode is operated in the reverse bias. So the negative sign is referencing basically the reverse bias operation. Do the steps make sense? Right? Load line analysis is pretty standard. We did it for the diode. We're doing it for the Zener diode. We will do it for the Zener regulator. And we'll also later look at it when we go into three terminal devices, right? You take your nonlinear device, isolate it, and you take your linear circuit. And your linear circuit means it's a linear line. So you can plot it and then apply linear analysis or load line analysis to any large circuit. So if we take these 2 points and we plot it here, we get this line right here. This is minus 15 milliamps and minus 15 volts. And the intersection of these 2 plots, this is for supply voltage as 15 volts. The intersection of these 2 plots is our solution. So coordinates of the intersection will give us the operating point or the voltage for the Zener diode and the current for the Zener diode. Yes. This one. That's an assumption on our part because it's a linear line on the graph. That means if we extend the line, it's going to this way. I always turn around. So if we take this plot and we extend the line, it's going to intersect the X and Y axis at some point. That would be the point where VD would be equal to 0 for the current, and then there would be ID would be equal to 0 for the voltage. So we plug in ID and VD is equal to 0, and then we find that corresponding coordinate for the other voltage or current. Okay. So the solution here is minus 10 volts and minus 10 milliamps. Oh, sorry, minus 5 milliamps. Okay, that's the graphical solution or graphical analysis. This is for VSS is equal to 15. Now, if the supply voltage changes, the supply voltage goes to 20 volts. Equations still remain the same, except now the values are minus 20 and minus 20 volts there. So if VSS is equal to 20 volts, my solution changes. Zener diode is supposed to keep the output voltage constant, right? That's the function, the primary function of a Zener diode in reverse bias. And so we can get the intersection point, and we can find VD is minus 10.5 volts, and ID would be approximately equal to minus 10 milliamps. Notice the change in the voltage and the current. The current increases by a large amount, the voltage with a very small amount. And even though you can see a change of 0.5 volts here, the reason is because the slope is exaggerated. Okay, real life Zener diodes, the slope is very steep. It's a near vertical line. The slope on the graph here is exaggerated. And so we see a difference of about 0.5 volts. The input supply voltage changed by 5 volts, but your output voltage does not change by more than 0.5 volts. Even in a real life Zener diode, it would not change, not even up to 0.5 volts. Okay. It's almost a near vertical line in the reverse bias. And so the output voltage remains constant. But this is an excellent example, right? The slope is exaggerated. We can find a different value. Input voltage increased by 5 volts, output voltage only by 0.5. Make sense? And that leads us into the primary application of a Zener diode, which is to be used as a voltage regulator. So now we add on, so we had our circuit with the Zener diode. We're going to add on a load resistor, and we will see how well the Zener diode can function as a regulator. Any other questions before we move on to the next example? So far, so good. Okay. All right. And this will be on Friday's quiz. Zener diode and Zener regulator. Okay. So Zener diode circuit. Now we added RL, a load resistor RL at the output. So RL is our load resistor. R is, of course, our series resistor. This resistor is sometimes also referred to as RS. Again, just depends on different books, different authors, different instructors, but it's basically series resistor. And then we have the total supply current, IS, that is coming from the supply voltage, VSS. Okay. So how does the circuit function as a regulator? So let me summarize right at the top. Okay. If I have IS coming from the top, has nowhere else to go except two pathways. One is through the Zener diode. So we have our supply voltage, we have our Zener diode, and we have our load resistor. Supply voltage goes into the load resistor and into the, supply current goes into the load resistor and into our Zener diode, right? There's no other pathway for it to go. Only two places. So if you apply KCL, I can state supply voltage IS is equal to IZ plus load current IL. Okay. IS is equal to IZ plus IL. Now, our application is that the voltage across the load resistor must remain constant. If VL is constant, that means IL must also remain constant. So far, good. Make sense? Right? VL must remain constant. Voltage at the output across the load resistor must remain constant. So IL, the current flowing through through RL, must also remain constant. What if our input supply voltage increases? What happens then? If VSS increases, what happens to IS? That also increases, right? Everything else is the same. So IS also increases. If IS increases, what happens to IL? Let's say a Zener diode is not connected. What happens to IL if a Zener is not connected? IL also increases. If IL increases, VL increases, which is not what we want, right? So we insert a Zener diode in there so that the extra current that is now coming from our supply voltage sinks through the Zener, leaving IL near constant. So if VSS increases, IS increases, and a Zener acts as a current sink. So Zener will sink the extra or the increased current. So the extra current or the increased current will flow through the Zener diode. It keeps the voltage constant. So the current to the Zener increases. If the voltage is constant, VL remains constant. So IL also remains constant. The only thing is IZ increases, meaning it causes an increase in the power dissipation. Right? It receives extra power now. IZ increases, VZ remains the same. So PZ, the power for the Zener diode, increases. And hence, every Zener diode comes with a power rating. Similar to a resistor that you would learn about in 201, every Zener diode also comes with a power rating. Well, actually, every device would come with a power rating. And so as stated earlier in this slide right here, PZ is part of the spec, the maximum power that the Zener diode can dissipate. And this is the reason why it's important. So P is equal to VI, standard power equation. So PZ is VZ times IZ. And hence, if IZ increases, PZ has a maximum limit. And you will see this at the end, towards the end of the solution of the problem. Okay. So let's analyze the circuit, perform a load line analysis. We are given a graph right here. This is the characteristic that is given to us. And we want to perform a load line analysis and see how well the Zener is functioning as a voltage regulator. So, question I would ask you is, what voltage is being applied to the Zener diode? If my VSS, let's say in this instance, I am given VSS as 24 volts, and R is given as 1200 ohms, and RL is given as 6000 ohms. What voltage is being applied to the Zener diode? Is it 24? So how do we calculate that voltage? Hence quiz 1. We need to determine the Thevenin and Norton equivalent circuits as seen by the Zener diode. You can't escape Messrs. Thevenin and Norton. All right, so what we are going to do is we are going to take our Zener diode, isolate in one side of the circuit. Okay, again, we are keeping the linear components on one side and the non-linear components on the other side. Okay, when I state isolate, doesn't mean electrically. Okay, I'm simply drawing it on the right side. It's a parallel connection. Electrically speaking, everything's still the same. Doesn't matter whether it's connected here or whether it's connected 2 feet away. It's still in parallel. It's the same electrical node, right? So I will draw the schematic, draw the Zener diode on the right side, isolate the linear components here, and then I determine the Thevenin circuit as seen by the Zener diode. So I can deduce the voltage that is being applied to that Zener diode. Okay. And so a Thevenin equivalent circuit, for our Zener regulator. Let's first find Thevenin resistance RT. What do we have? I would first, actually, let's draw this. I have VSS, my supply voltage. I have the series resistor R. And I have RL. And these are my terminals of analysis. Remove Zener diode from my analysis. And I want to find the Thevenin equivalent circuit between A and B. Okay, between A and B. So now we can go in and analyze for RT. Now let's take a pause. Let me know if you have any questions before I begin. So far, so good. Okay. RT, Thevenin voltage, is simply Req. So what happens to the voltage source? Current sources and voltage sources are reduced to 0. So voltage source is replaced with a short circuit. Current sources with an open circuit. If I short it, what happens to the relationship between R and RL? They are absolutely in parallel. And so RT, which is measured between A and B, is simply the parallel combination of R and RL. It simply means R times RL, product of the two, divided by the sum of the two. 1200 times 6000 divided by 7200 gives us nice even round number of 1000 ohms. Okay, that's the Thevenin resistance. And then Thevenin voltage, VT, go back to the original circuit, plus minus VSS R RL. And analyze again between A and B to find VT. Any guesses on what technique we can use? Well, yes, but that would be, yeah. In this case, it's one mesh. So yeah, one equation. Yeah. But again, Ohm's law, KVL, KCL, these are the only three, right? So if you take a look at the circuit, it's VT between two terminals. We are simply measuring the voltage. If you're simply measuring the voltage, that means there is no component connected at that node. There's no component connected between R and RL. It means they are in series, indeed. And if they are in series and a voltage is being applied, what technique comes to mind? You can use Ohm's law, apply it twice, or shortcut voltage division. That's it. 201, three techniques. Ohm's law, KVL, KCL. That's a default answer. Right? Everything else is derived from these three. So Ohm's law, you can apply Ohm's law twice and find the voltage, or you directly apply voltage division. If you apply voltage division, I can write the equation directly. I can write VT is a fraction of VSS. The fraction is given by RL to the ratio of R plus RL. And so that again is 24 volts times RL is 6,000 and divided by 7,200. Oh. And that gives me a Thevenin voltage of 20 volts. Just on a separate point. So mesh would entail the same thing. You write a mesh equation, that would be a KVL equation, and we'd end up getting the same result. So it's one equation. So while you write it down, a couple of observations. We are applying a certain amount of voltage. In this case, VSS is 24 volts. That 24 volts is being split across R and RL. Okay. And Thevenin voltage, VT, that is the thing that is being applied to the Zener diode, right? It has both R and RL in that equation. So depending on the values of R and our load resistor RL, the output voltage that is going into the Zener diode may be lower than the Zener voltage. And if it is lower, then the Zener diode would not turn on. Again, I'll repeat. We have VSS, we have our series resistor R, and we have a load resistor RL. And both of those resistor values are present in the equation for our Thevenin voltage. That's the voltage that is going as input into the Zener diode. So depending on the values of R and RL, the voltage that is going into the Zener may be lower than the Zener voltage. And if that happens, then the Zener diode is effectively redundant, or more appropriately, may as well not be present in the circuit. It will not turn on. So there is a limit. There's a minimum limit and there's a maximum limit for every single quantity. Okay, so there is a minimum limit for the supply voltage and a maximum limit for the supply voltage. There's a minimum limits. There are minimum limits for the series resistor R and RL, and there are maximum limits for R and RL. And we'll look at all of those. Well, actually, not all of those. We'll look at for supply voltages once we finish our load line analysis. Okay. So our circuit now looks like this. Actually, it looks like this. We have Thevenin voltage VT, and we have the Thevenin resistance RT, and our Zener regulator connected to it. The reference polarity, again, instead of taking VZ and IZ, goes into diode voltage and diode current. So that is in reverse bias. So it's opposite of the Zener diode VZ and the Zener current IZ. So if we apply KVL to determine the line, the load line for the circuit, this is the expression we would obtain. So we have this, and let's make a line here. I'm going to continue load line analysis on this side. We'll perform the other analytical analysis on the other side. We'll apply KVL. And this is to figure C. Doing on time. Oh, and better speed things up. Okay, so VSS is 24 volts, R is 1.2, RL is 6 kilo ohms. And the question being asked, I've done that earlier, is find VL, output voltage, and then also determine the supply current IS. Okay, output voltage and supply current IS. So I would get minus VT minus VR minus VD is equal to 0. And therefore, I can write an expression for VD and VR in terms of ID times R minus VD is equal to 0. Two unknowns, ID and VD, to find the endpoints of the line or the intersection points with the X and Y axes. I would plug in VD is equal to 0 volts. And therefore, ID would be equal to minus VT over R. Yes. So that's because I apply KVL in this manner, and I simply take, so my method of applying KVL, the question being asked is why are the negative signs everywhere? There's 2 points to it. One is the reason the way I apply KVL is I take all the voltages in a circuit, let's say VT, VR, and VD, and sum them up to 0. This is the way I apply KVL. Okay. But simply stated, one supply voltage must add up to the to the resistor voltage VR and the diode voltage VD. Right? There's one source in there. So if you're applying KVL, logically, the supply voltage is being dropped across the load resistor, the series resistor and the diode voltage. So when I apply it, I take minus VT, and because my current is flowing in this direction, I get a plus minus sign this way. And I sum up the voltages in a clockwise manner. So I get minus VT minus VR minus VD. If you apply it in a counterclockwise manner, you would get VT plus VR plus VD is equal to 0, which is again the same equation. And the minus sign for the diode and the resistor is because it is operating in reverse bias. Because it's an operating in reverse bias, that's why it's minus. If I was to simply just say supply voltage is equal to resistor voltage plus the diode voltage. So it would be VSS is equal to VR plus VD. That's it, right? There's one source, one voltage. All right, so I have minus VT over R. ID would be equal to, let's see, 15 minutes. All right, VT is minus 20 over R. So that gives me minus 20 milliamps. And if ID is equal to 0 volts, then VD is equal to minus VSS, which is minus 20 volts. I have the two ends of my line. Go ahead and plot it on the next slide. And when I do that, I get a line that intersects the diode characteristic at this point. And the coordinates for this point give me the solution. And that turns out to be minus 10 volts and minus 10 milliamps. And again, the minus sign is just because we are in reverse bias. Okay. If you think back to earlier in this chapter, we performed load line analysis of the diode, regular diode in forward bias. Everything was positive because we were in the first quadrant. Positive voltage, positive current. Now it's negative voltage, negative current. Just reverse bias. That's all it means. So the load line analysis doesn't change. That remains the same. Okay. For all devices, it remains the same. But do you have a question? Where? Oh, let's see. Oh, this one. I did that in the previous section too. So ID is 0 amps. Yeah, thanks. Okay, let's, so that was the graphical analysis, okay? Let's do some analytical analysis on this. So if we have a load regulator, the possibilities for the questions, again, can be determine the range for R, determine the range for RL, determine the range for the applied input voltage. Let's look at input voltage because that's the most important, right? How well can the Zener diode function as a regulator within certain limits of VSS? Okay. So if VL, in this example, VL is desired to be 10 volts, then we need a Zener diode of 10 volts. So if the requirement is that VL should be 10, then VZ, our Zener diode, should also be 10 volts. Then what is the range of VSS that the circuit can withstand, or the Zener diode can withstand? Okay. So if I was to analyze the circuit, let me redraw it first. In the range of VSS is the question mark. So I have the supply voltage VSS, series resistor R, my Zener diode. And this time I'm simply going to take load resistor VL, load resistor RL, and reference the voltage that's in parallel as VL. Okay, this time I'm not looking specifically at the diode. I'm looking at the circuit. So I'm taking a step back and looking at the circuit, not looking at the diode. Diode voltage would be negative, diode current would be negative. But in this case, I'm only interested in the load voltage and the load current. So it's all positive. IS comes in this direction from the power supply, goes through the load resistor R, and splits in two. This is IL, and this would be IZ. KCL at the top gives me IS is equal to IZ plus IL, right? Now, if I want to find the minimum value for VSS, I need to find the minimum value for VSS. Going back to the point I was making earlier, one supply voltage and two passive components, resistor and a diode. So logically, we can write supply voltage VSS is equal to VR plus VL. Make sense, right? So VSS is simply equal to VR plus VL. Now, how can we find VL? Well, again, voltage division, right? VL is across that load resistor RL. And so from voltage division, it's a fraction of VSS. So VL is times RL divided by R plus RL. If I rearrange the terms, I can find VSS min. So VSS min is VL times R plus RL divided by RL. My desired voltage VL is 10 volts. So it's 10 times 7200 divided by 6000. And thus, the minimum voltage that the supply needs to source is 12 volts. If the supply voltage falls below 12 volts, the voltage being applied to the Zener is less than 10. It would not turn on. And that's why values for R and RL are critical. If R value is large, then VL is going to be smaller than 10. That's why we need a minimum value of that voltage. So again, this is where R is given to us, so we are determining VSS. Another approach to this would be if VSS is given and we are trying to determine the minimum and maximum values of R. That's another approach, the same aspect of the design problem for a regulator. Okay. All right, about 7 minutes left. Let's get through here. Now to find the maximum range, we need to, let's say, use a typical Zener diode that would have some power rating. Okay, but just to show you a large variation, I'm going to choose a power rating of, let's say, 1 watt. Very large number, right? So let's assume PZ or PZ max is equal to 1 watt. If PZ max is 1 watt, given that VZ is 10 volts, we can determine IZ max, meaning the maximum current that the Zener diode can handle without exploding, right? Thermal power dissipation. And so IZ max is 0.1 amp or 100 milliamps, which is a huge number. Like typical current values, especially what you use in the lab, would be a few milliamps or less. Okay, 100 milliamps is a large number. So if IZ max is 0.1 amp from the above KCL, we can find IL or IL max. IL can also be determined by Ohm's law, VL over RL. And that gives me 10 over 6,000 or 1.667 milliamps. Right, from Ohm's law. Now at this point, I have the current flowing to the Zener. I have the current flowing through the load resistor. I know that the load current must be kept constant. That cannot change. That is the objective. So it has to stay or it has to remain at 1.667 milliamps. Any extra current that comes from the supply must go through the Zener. but that maximum limit is 100 milliamps. So that means that the maximum current that can come from the supply cannot exceed the sum of these two. Does that make sense to everyone? Right? KCL. And so IS max cannot exceed IL plus IZ max. That comes out to be 101.667 milliamps. And IS cannot exceed this maximum value. Okay. IS cannot exceed that maximum value. And then if this is the maximum current that can come from the power supply, what is the voltage across that resistor? VR. Because that is in series with the power supply. So all of this current, 101.667 milliamps, must go through this resistor R, which causes a voltage drop across that resistor. And so I can write VR is equal to 101.667 milliamps times, what's it, 1200, gives me a value of 122 volts. So the series resistor at the maximum limit of the Zener diode will drop 122 volts across it. Large number. And that means that VSS max cannot exceed VR plus VC or VL, excuse me, which is 132 volts. Therefore, final summation is that the range for VSS is 12 volts up to a maximum of 132 volts. All right, questions. Let it all sink in and let me know what questions you have. Do the steps make sense? I'll give it another 30 seconds. So the other probable questions based on this can be, and I'll summarize these here. So possible questions. We are coming up on 2 o'clock, so if you need to leave, feel free to leave. This will all be posted anyway. Possible questions here is a design problem where supply voltage could be given and you'd be asked to find RS minimum or R minimum and R maximum. And you'd have a range for RL minimum, the load resistor, and RL maximum. Okay. This was the result because we chose a Zener diode of 1 watt dissipation. If we choose a Zener diode with half a watt of dissipation, the maximum range would be reduced, right? So as a designer of this regulator circuit, that would change. Okay. All right. So with 30 seconds over 2 o'clock, we'll end class here today. Quiz on Friday. 90% of it will be Zener diode and Zener regulator. And then homework would be due. So the due date is already there. Make sure you you keep up with the due dates. And then Monday quiz will be based on Monday, Wednesday, Friday of this week. Okay. Does anyone have any questions before I shut this down? Okay.